Okay, in this lesson, we're going to talk about what it means to be polar. So, in order to start our discussion, I'm going to go ahead and draw 4 boxes. Now, in box number 1, I'm not going to draw anything. It's just a neutral molecule, just a completely neutral molecule, no plus minus anywhere to be seen on that molecule. Now, in box number 2, I'm going to draw a plus sign. Box number 3, I'm going to draw a minus sign. And in box number 4, I'm going to draw a plus sign and a minus sign. Now, if I asked you which one of those boxes represents a polar molecule, well, let's take a look. In this first one, we have a completely neutral molecule, and there is no separation of charge anywhere within this molecule. Perhaps this is like a hydrogen molecule where an H is bonded to an H. H, having the same electronegativity as another H, means that they both pull equally hard on the electrons in this bond, so the electrons do not get pulled towards one side or another. This is not a polar molecule. This, in fact, is a non-polar molecule. Okay, now let's look at box number 2. In box number 2, all we have is a plus charge. So this, in fact, is just an ion. This is a charged particle, better known as a cation here, being a plus charge. Now that is not a polar molecule. That's not what it means to be polar. In box number 3, all I have is a negative charge. That is also an ion. It's called an anion. And that is not what it means to be a polar molecule having charge. However, in box number 4, what we see here is that there is a separation of charge. One end of the molecule has a different charge than the other end of the molecule, a plus on the left, and a negative on the right. That is what it means to be polar, having a complete separation of charge. So here's an example for you. We say that the Earth has poles on it. When we draw our Earth, we have a north pole, and then we have a south pole. One end is opposite of the other end, north-south. Magnets are also considered polar because they have opposite poles, north on one end of a magnet, south on another. If we have 2 opposite ends, then we're going to be called polar. So what could give us a polar molecule? Well, an example of a very, very easy one is something like HF, hydrogen fluoride. If we look at the HF molecule, fluorine pulls much harder on electrons than hydrogen. Fluorine has an electronegativity of like 4.0, whereas hydrogen has an electronegativity of about 2.1. Fluorine's going to pull much harder on the electrons in that bond. So the electrons are going to be pulled towards the right. If there is a pull on this bond, this is a polar bond. If the electrons are shifted to the right, that's going to leave this side of the molecule, the hydrogen, a little bit positive over here because the electrons went over here. It's a little bit electron deficient or positive. This side of the molecule, on the other hand, will be charged a little bit negative. We have a molecule with a positive side, a negative side. That is a polar molecule. We have a polar bond in a polar molecule. Now, things get a little more tricky, however, if you're not just talking about 2 atoms. 2 atoms is pretty simple. For example, if you have H with H, the electrons are not pulled one way or another. That is non-polar. But if you have HCl, Cl has a different electronegativity than H. The electrons are pulled towards Cl. That is a overall polar molecule. It's a polar bond and a polar molecule. This side would be a little bit negative and this side would be a little bit positive. Another example of a nonpolar would be something like F and F. Fluorine, although it's very electronegative, pulls just as hard as the other fluorine. Nobody wins, no pull. That's a nonpolar bond, and that is a nonpolar molecule. So how does it get trickier? Well, what if there aren't two atoms involved? What if it is 3, 4, 5 multiple atoms involved? Then you have to look at the individual tugs of war for the electrons on those atoms and decide, does anyone win the overall tug of war? So in the videos below, I'm going to go through each of those electron domain geometries: trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, and we'll look at all the different circumstances for whether the overall molecule is polar or nonpolar based on the polarity of the bonds. And this whole idea of polarity is extremely important. If a molecule is polar versus nonpolar, it's going to affect whether it sticks together very well, whether it stays together as a solid or easily turns into a gas. It's going to affect how it dissolves in different fluids. So we're going to learn about that when we study intermolecular forces, but for right now, let's just try to decide, is a molecule overall polar or nonpolar?